Let's look at some non-ideal effects in our transistor current sources. Primarily, let's look at our output resistance and our early effect. So we know if we have a finite output resistance from our transistor current source, then if we increase our VCE voltage, that's going to result in an increase in our collector current IC. And so as we recall from discussions of early effect in previous classes, we can show that graphically as shown here, where we plot our current on our vertical axis and our collector emitter voltage on our horizontal axis. And in the ideal case, we would draw this in such that the blue line is horizontal once we raise our voltage above the VBE on value, which is typically 0.6, 0.7 volts. But if we consider our early effect, we see that we actually have a slope to this blue line, and the slope of this blue line in our forward active region is equal to 1 over the output resistance R0. Now, our early voltage comes into play if we extrapolate that blue line back to our horizontal axis, and we see it intersects the horizontal axis at a point negative VA, where VA is our early voltage. So our early voltage is equal to VA. So if we are not considering our early effect, so no early effect, then what we're going to see, and like we in fact did see in our previous example, is we would have VA and R0 equal to infinity. And so that means also that we have no slope in our line above. So no slope in our IV plot in that forward active region. Okay, so what changes if we do consider our early effect then? So considering our early effect, what's going to happen is our current IC is going to be equal to whatever our original current would have been without considering early effect, plus some portion that's multiplied by VCE divided by VA, where VA is our early voltage. And so this IC prime value is what our collector current would be without considering early effect. Okay. And so what we can see is this kind of reinforces what we saw graphically above. If we are increasing our VCE voltage, so we're moving further to the right along this curve, so maybe we start here, we move towards the right, we see that as we increase our VCE, our current is also increasing. And so that's accounted for with this VC over VA term in this equation here. And so again, the IC prime is the original collector current without considering the early effect. Okay, so now let's look specifically at the equations that we had for our two transistor current source. So our two trans current source. And so what we're going to do is we're going to make an approximation that we often make when we're dealing with these types of transistor circuits, is we can essentially neglect our base currents because they're going to be much smaller than our collector currents. So let's say neglecting our IB1 and IB2, and we can do that because typically, remember, our beta values are very large, and of course we have IC is equal to beta IB. So if our collector current is 100 or 200 times larger than our base current, then we could say that our base currents are approximately negligible. And again, we can do this for sort of first run calculations, and then if we need to refine it, we can update our calculations from there. So neglecting our IB1 and IB2 for our two transistor current source, we can then say that the collector current for IC1 is approximately equal to our reference current, IREF. So what we can say from there, if we want to include this early effect, is, well, we can say IREF is equal to IREF prime, so this would be our IREF without considering the early effect, times the quantity 1 plus VCE1 divided by VA. So I've essentially just adapted this equation up here to fit for our transistor Q1, which was on the left side of our two transistor current source. We can do the same thing for the transistor on the right side. We can say IC2 we had labeled as I out. So we can say that is equal to I out prime, so whatever our original output current would have been without considering the early effect, times 1 plus VCE2 divided by VA. Okay, so now what we can do is we can look at the ratio of these two. So if we're interested in the ratio of I naught divided by I ref, and so we'll see where, I know it kind of seems like I'm going off on a random tangent, but we'll see where I'm going with this here in a little bit. So if we take this ratio using these two equations above, what we'll see is this is I naught prime divided by I ref prime times, now we have a big fraction here, and in the numerator we have 1 plus VCE2 divided by VA, and in the denominator we have 1 plus VCE1 divided by VA. But from a previous video, we know this equation here, because remember what this is without considering our early effect. So if we're not considering our early effect, we know that I naught prime over I ref prime, we had found that that's just equal to 1 over 1 plus 2 over beta. So that would be our standard equation without considering the early effect for our two transistor current source. Now from the configuration of our two transistor current source, we also know that VCE1 is equal to VBE1, which is just equal to VBE. And so the reason that we can say that is this is true because for our transistor Q1 on the left, we had our collector and our base shorted. So that means that that condition is true. And this is true because we did that KVL around the bottom loop. There's no resistors, nothing else in there. So we know that our VBE1 is equal to VBE2. So we can just simplify and call that VBE. Okay, so if we update our equation up here with these two new additions here, we can simplify this a little bit. And we can say that our I naught divided by I ref is equal to, so we have 1 over 1 plus 2 over beta out front. And now doing some algebra, we can rearrange what this would have been if we substitute in VBE for this VCE1 here. We're going to substitute that and do some algebra, and we're going to have 1 over 1 plus VBE1 divided by VA plus another fraction, and we're going to have the same denominator, 1 plus VBE1 over VA. And in the numerator of this one, we have VCE2 divided by VA. Okay, so we get this really messy equation, and I'm going to label this as 3 to be consistent with our notes. So what are we going to now do with this? Why have we gone through all this trouble? And so what we can say is ultimately what we want to know about this two transistor current source is we want to know how much our output changes as our voltage across that transistor changes. So we want to know how I out changes as our VCE2 changes. And so we'll see, I'll draw up a circuit here in a little bit, but some reasons why our VCE2 voltage would be changing relate, of course, to what is happening in our load circuit. So mathematically, if we want to find the change in I naught as some other variable is changing, we can of course take a derivative. So we can say we can find this by saying, well, let's take the derivative of I naught with respect to VCE2. And so of course we can do that with this equation up here. all we're going to do is we're going to multiply this IREF, we're going to put it on the right side, and we notice that everything else is a constant. The only place that we have VCE2 is right here. And so this whole first term here is a constant, so that's going to go away. So we're going to be left with just this second term, and we can essentially think about it as just pulling VCE2 out front so that we just have 1 over VA divided by 1 plus VBE1 over VA. And remember, I can also simplify to just VBE because we know both of the VBEs are the same. So doing that, we're going to be left with IREF, so that came over from the other side, divided by 1 plus 2 beta, so 2 over beta, so that was that term that was out front, and then taking the derivative of the term in the fraction, or sorry, in the parentheses, we have 1 over VA divided by 1 plus VBE over VA. Okay, so now we can make an approximation, and we can say, well, typically our VBE is going to be much less than VA. And so we had talked about this previously when we talked about early voltages, but we know typically that's going to be a large value because normally the slope in this line here is relatively small. And so graphically we can think if that slope is small, this is going to take a long time if we're extrapolating back this way before we intersect that horizontal axis. So typically on the order of 100 volts, give or take a little bit. So compare that to values of our VBE voltage. So remember, this is going to be our VBE on, which is typically on the order of 0.7 volts. So we're comparing, on the order of 0.7 volts to about 100 volts. So that's a pretty big difference. So if we do that, we can simplify this a little bit, and we can say that our di naught with respect to VCE2 is equal to approximately, so we still have that front term, IREF, divided by 1 plus 2 over beta, times 1 over VA. So our whole denominator here is going away because this term is essentially 0. If we consider this. Okay, well, so now we can say our IREF divided by 1 plus 2 over beta, well, that looks really familiar. That's what we had defined as our I naught prime. So that was our output current without considering early effect. So this right here is without considering early effect. And then, of course, we have just the 1 over VA from our second term. And we know by definition, we're talking about changing current with respect to voltage. So that's going to be 1 over a resistance. And so that resistance, R naught, is going to be our small signal output resistance at our collector Q2. So our R naught is our small signal output resistance at collector of Q2. So we can see our output resistance of our 2 transistor current mirror is just the small signal output resistance of transistor Q2. And we'll talk a little bit later on about how we can improve that and why that's not ideal. If you want to see an example of how to use this equation right here, I would direct you to page 691 in the Niemann Microelectronics textbook. So if you look at example 10.2, that's going to show you how to use that equation. But for our purposes, the main thing I want you to take away is that our output current is changing as our VCE2 is changing. So that's sort of the main takeaway here. And so what does that look like? Well, let's take a look at sort of a circuit here. So let's say we have this circuit, and let's say I'm going to put in a load circuit now. So before we just had a ... to load, but now let's say we actually put in a load circuit, which is just a single transistor. So kind of like we saw in the very first video on this topic. So let's say we have something like this, and here, and we just have on our base, our input, VI, and maybe we have some resistor up here, and then this is going to be connected to the same voltage on this side. So we have RC, and this is our output voltage defined at the collector. And so we can call this Q naught, and everything in blue there is our load. So the black would be our current source, which is supplying our current to this load transistor Q naught. And so of course we could write in here, this would be our I naught. So we see how the collector current from Q2 becomes that current that's biasing our emitter current, which is essentially equal to our collector current for Q naught. Okay, so we could also think about how things are changing as our input voltage changes. So let's label this as VBE 0, and let's label our VCE 2. So what we can see is that if our VI is changing, our VBE naught should be relatively constant. So this value here is going to be relatively constant at our cut-in voltage, so that's going to stay about 0.7. So as our VI is changing, something has to give, and so that something is going to be our VCE2. And so now we know if our VCE2 is changing, ultimately that's going to lead to changes in our output current. And so we're going to come back and we're going to talk about this topic a little more, and we're going to compare how different transistor currents sort of compare to this in terms of output resistance and performance. But as always, if you have any questions about this video, please don't hesitate to let me know.